In this video, we will talk about distributed data engines and how they are able to analyze massive amount of operational data. In a previous video, we discussed what's a data engine. It is a processing unit that's able to take in very complex, very high speed, raw operational data, clean that data, validate it, transform it, which is often called a data pipeline operation, then fuse the different data streams or the events within the data streams together and performs an analytics on it and generates very meaningful, comprehensive events. The events are not the final intelligence. They are the fundamental blocks that enables data analysts or engineers to work on the final data intelligence in both operational intelligence, which is typically real-time type of intelligence, or business intelligence, which is typically based on batch or historical analytics. So what we discussed before is that a data engine is really able to reduce both data volume and data complexity. This is because raw operational data can come in with many data tags and at very high speed. So for example, in a typical manufacturing environment, you can have hundreds and thousands of data tags per system. And the data tags can coming in every second or every 10 seconds. So there's a lot of data that gets generated, and it is very hard actually to derive very deep meaning out of it simply because amount of data available. So a data engine, that's what it does. It derives the events, right? So for example, maybe it looks at all the data available and figured out, oh, there is a production run going on and the result is successful. The runtime is 32 minutes. Who is the operator? What are the different warning codes or error codes? What's the efficiency of the test, etc., etc. These events are much more rare as compared to the raw data. Sometimes it's one event per hour or even one event multiple hours. Therefore, you're reducing the amount of data by thousands or tens of thousands of times. But you're also reducing the complexity because you're converting the raw data into meaningful events, which, as many of you will recognize, is kind of like a structured type of SQL data, right? That's very easily digestible by BI software. So a data engine is very powerful in analyzing that data. Now, let's talk about distributed data engines. Distributed data engines is a technology where you can deploy data engines either in different locations, for example, in the clouds or on-premise, and you can deploy them multiple data engines per even a particular type of data stream. For example, if you have thousands of data tags stored in Snowflake, you may not be able to process all that in a single data engine. So you may split the task into multiple data engines. So data engines should be able to be deployed, scaled to many instances, either in a single location or across many different locations. That makes the data engine very powerful in producing events, which eventually gets combined into comprehensive insights. And that allows you to analyze hundreds of thousands of data tags to get insights out. And obviously, the events are typically not the final answer. The events can be fed into a BI software that allows you to look at aggregates, statistics, to finally produce the reports on the various metrics you're interested in. So this is how a distributed data engine allows you to analyze huge numbers of data tags from all sorts of many different locations in your system. So let's look at some example systems that can be used, data engine can be used to analyze. One example is in oil and gas, in the drilling industry where, say, you're analyzing a mud pump. A mud pump is a multi-million-dollar machine, and there's a lot of sensors, and the internal data comes out of the mud pump that allows you to analyze the operation of the mud pump to prevent downtime, to improve the efficiency. So if we look at the kind of data that describes the mud pump, they can include sensors, external vibrations sensors, for example, that monitors if the vibrations are normal or not. Electronic drilling recorder, or EDR, that's an internal sensing element inside mud pump. And they monitor almost every component inside the mud pump. And there's a lot of data. Many of the data tags in the EDR can stream as fast as every second. Work logbook, that's a digital logbook maintained by the drillers. Whenever they inspected the components, replaced the components, they put those information in the work logbook. Operational software, those are the softwares the drillers use on site to control the mud pumps as well as other equipment. And the operational software provides a huge amount of data on how every equipment works. So as you can see, there is a lot of data on this type of machines, and the data are also distributed in different locations. Some of them are already streamed into the cloud. Some of them are still on site. So you have to be able to deploy data engines to different locations and possibly multiple data engines in the same location in order to analyze a huge amount of data available. So what are the events that we're looking for from the raw data? Where we're looking for alerts that comes from any of the data streams, and we wanted to understand if the alerts are real or not. Very often today's systems can generate thousands of alerts per data source per day, and there's no way a operator or a driller is able to go through that. So you wanted to use the data engine to figure out if the alerts are real or not, and reduce that into a small number so a operator or driller can handle that. You are interested in the run states of the mud pump. The mud pumps are not always on, right? Sometimes you have to take them offline, and either for maintenance or to prepare for the next operation. So they can be off, they can be on, and they can also be under stress. Under stress is when you're running pressure or the speed of the pump over the typical range. That causes a lot more potential damage to the mud pump. So you wanted to know those events. And obviously any maintenance work, component replacement you've done on the mud pump, so that you can keep track of how new the components are. So what are the BI analytics you wanted to work on, right? So now instead of working on the raw data source, which is huge and pretty much unmanageable by BI software, you can now work on the events extracted. So for example, one of the important BI you wanted to work on is component running hours. How many hours have each component been operating, right, since the component replacement? So clearly you have to look into the work logbook to figure out when the component is replaced. You look at the, say, pressure data to figure out when the component what have been on, and then you figure out the stressful times. Then maybe use some kind of a metric to determine how that translates to effective component hours, and finally figure out what are the effective hours. And once you know that, you can alert drillers once a component gets close to its end of life before the component breaks down. That's very important. The stress interval is very important because the stress is very bad for these machines. So you can use stress to predict potential failures. And you wanted to look at the top issues, right? Very often for a driller who's working on site, they fix issues as they appear. But if you're able to collect all the issues from all the sites, all the machines, now you can actually understand what are the top problems the machines are having, the drillers are facing. So that enables you to solve those problems. Mud volume is another important one, because ultimately mud volume is like the total throughput of the system. So by understanding, how mud volume is determined by all the different components, different configurations, you can understand how the machines work and you can improve that efficiency. So this is a very complex set of tasks to do, but by converting raw data into events, it enables you to work on BI analytics much more easily as compared to working on BI analytics directly on the raw data. So let's look at another example system, right? This is a instrumentation type of system where, say, in each lab, you can have tens or hundreds of analytical instrumentation. All those instrumentation are connected together to a data engine which collects status data from the instruments and performs analysis on it. So the data source in this case is essentially include the instrument status messages you collect. But the messages themselves are only instantaneous reading on the instrument. That's really not what the events are. The events in this case are basically tests, right? So if a test has been performed, what's a runtime, what's a status, success, failure, other conditions, what's the product that's running in the instrumentation, what are the different error codes, who are the operators. So those are the properties of the test event. So what you want to do is you want to collect the raw data, generate test event from the raw data, and generate that from a single lab, then aggregate that across different labs. So now with that events, you can do a lot of BI analysis. For example, you can understand the throughput, total throughput of a lab, throughput of a particular machine, throughput across different labs. You can understand utilization and efficiency, right? Utilization is how much the instruments gets used, and the efficiency is how effective they are in producing successful tests. You can understand the top errors, right? What are the top errors that you encounter during the tests? And that'll tell you, if there's things you can do to reduce those errors. You can understand operator performance, who's doing well, who needs training. You can understand lab performance, which lab is doing well, why is that the case? And if some labs have extra capacity, so you can move some of the jobs, maybe from a lab that's full, so to improve the overall efficiency of the entire organization. So by collecting the raw status data, you can generate tests. And from the tests, you can do a lot of BI analytics to understand everything about how you are operating with the instruments. So another very basic use case is using a distributed data engine as a distributed data pipeline, right? So you typically have a BI software and you wanted to access all the data that that are available in your organization, but because the data may be distributed, in particular on-premise, is you cannot get them from the BI software because they're in different networks. So in that case, what you can do is you can deploy data engines to all of your different locations and collect that data sources through a data pipeline operation, and then send that all into a data warehouse. That makes all the data available to your BI software. So this is interesting because obviously a lot of BI software assumes that the data is available, which is often not the case for operational data. So the data engines would allow you to collect all the data into a data warehouse to make it accessible. Another very interesting topology, a related topology, is instead of sending all the data sources into a data warehouse, you simply make a data connector that enables you to just gather whatever data you need into the BI software. So notice the difference between this scheme and the previous scheme. right? So in the previous scheme, you have to gather all the data first into a data warehouse. And because often you don't know what data you're going to use, you're going to collect as much data as possible into the data warehouse ahead of time, right? But in this case, the BI software, looking from the BI software perspective, it's like it's able to access all of the data sources because essentially each BI software's data connector is connecting to what it thinks are the data source, even though that really is sort of a virtual data source that relays the BI data connector commands to the actual data sources, which may be distributed in many different locations. So that way you can collect the data you need from the data sources through this architecture. So it's very efficient. It's as if the BI software has access to all the data sources in the same network configuration. So this is also very powerful and very useful. So these are some examples of how you use distributed data engine to make data accessible, to make data useful, and also to ultimately produce the data insights that's required in enterprise operations. If you have any questions, please contact us. Thank you.